So good morning, everybody. So today we are starting with chapter number 10, and the title, as you can see, is Electromagnetic Wave Propagation. Now, this is a pretty long chapter, and I have, because of the length of the chapter, I have divided the PPTs into three parts. Okay, there will be a chapter 10A, 10B, and 10C. So in 10A, let's see what we will be doing. Even before that, let me talk about the objective of the chapter. Okay. The objective of the chapter is a discussion on electromagnetic wave propagation in different types of media. Okay. So when I'm talking of different types of media, I will also be talking about the four classification of media and how the electromagnetic waves propagate through these media. And then what is the relationship between electric field and magnetic field? What would happen to the wave when it propagates? All these things will be part A. Now coming to part B will be polarization of waves. In electromagnetic theory, polarization, the concept of polarization is very important because your antennas and everything for that matter, your FM radio, your AM, everything is dependent on your polarization of the wave. So what is polarization? That will also be taught. And when I am teaching that, what happens is, I have seen the material given in your book. It is a little preliminary. I wanted to go a little more than that. The reason why I wanted to generalize it a bit and give you something slightly more. Okay, the reason is because if you are going to have this course called antennas and wave antennas, you will require certain things which are not there in this particular section. So that's the reason I have slightly deviated from the book. And then, of course, we will also be in part B talking about our considerations in propagation. So, because we have already discussed that, when we are talking about the propagation of the wave carries energy also, energy and information. So, when we are talking of energy, rate of doing work, energy is related to power. So, we will talk about power considerations. And part C will be reflection and transmissions at the boundary of two medium. You have a medium 1 and a medium 2. So what would happen? What part of the wave will get reflected? Will it get reflected in all kinds of mediums? Will it get transmitted in all kinds of mediums? And what will be the ratio of the part that will get reflected and what gets transmitted? So that will be discussed in part C. So now we are going to start off with part A. So it's how uniform plane waves will travel through different unbounded, homogeneous, isotropic medium. So these words are all clear. You know what is homogeneous, you know what is uniform and isotropic medium. Okay, so we are talking about unbounded. So when I'm talking about unbounded, what I mean is there is no boundary at all. You may be talking about propagation of wave through space. So that's an unbounded medium. Okay, so we are talking about that in this particular portion. So now before we go ahead, I want you to recall some things that we have studied, what would be required for this particular chapter. So one thing that you're going to require is the mathematical representation of electromagnetic wave. So this is something that you're going to again and again refer to. Okay, and more specifically, we'll be talking about the phasor form, phasor representations. Last time also, when we just introduced it in the previous chapter, I said we will use it in chapter number 10. So this is where we are going to use it. So like for example, if you have the electric field of an electromagnetic wave as E, a function of z comma t, is E naught and a cosine function omega t minus beta z with the electric field along the az cap direction. That means it is having only the z component, but it is propagating along the positive z direction. If this is your time harmonic form of the electric field, it can be represented in the phasor form you have seen previously as the real part of Es e to the power of j omega t. Okay, like for example, that e to the power of j omega t, for example, can be written as cos omega t, okay, plus j sine omega t. So this is simply the logic for writing a cosine function as a real part of an exponential. So here when we are talking about ES, we are talking about the phasor part of the electric field, and the phasor part I have mentioned, it will be only a function of position. It will be only a function of position. Time is taken out separately. Time is taken out separately, and you can use my cursor. Yeah, time is taken out separately. We have put your time as e to the power of j omega t. So the phasor part is going to be only a function of z, but of course it will have its direction. Okay, so this is the phasor representation. Now you can see here that if Es is equal to E naught e to the power of j beta z, then you can talk about the real part as real part of Es will be E naught, okay, cos of minus beta z along the ax cap direction. Now, if you want your ES in the harmonic form, then what should you do? ES in the harmonic form is going to be E as a function of z comma t will be equal to this one. And of course, you're also going to have that e to the power of j omega t. So that also will come into picture. So omega t minus beta z along the ax cap direction. I hope this is clear to you. Any doubts? I hope this is clear to you.
Yes, ma'am. Please continue.
Yeah. So this kind of phasor, and please remember, when you're talking of a wave, it need not always be the real part. Sometimes it can be a sine function also. Okay. Or sometimes it can be a combination also. Those things we will see as we go along. In the last chapter, we tried to keep it as simple as possible. It was a pure sine function, a pure cos function, or you had a exponential form, or you wrote different forms of cos A plus B. So those were the types of problems that you have seen. Now, the next thing that you should remember will be your Maxwell's equation. So again and again, I don't want to repeat that. So Maxwell's equation in the differential form and the integral form, you should be familiar with. Now, going ahead, what are the other things you should know? You should know to use Maxwell's equation to calculate unknown parameters, which you have done in chapter number 9. Then you should remember the boundary conditions that you had written for electric field and magnetic field. Of course, that you have studied in detail in the previous chapters. Then, what are the other things you need to know? If I'm talking about a sine function or a cosine function, you should know how the graphical representation would look like. Okay, like for example, here you are having a sine function. How the graphical representation will look, and then what is the meaning of lambda, okay, and what is the relationship between lambda, propagation speed, and the time period. Very elementary. Then you should also know u equal to 1 by under root of mu epsilon. Okay, this you can, I would like you to just remember c equal to 1 by under root of mu naught epsilon naught. So this will help you remember this particular formula. The relation between the permeability of a medium, and the speed. Then of course, you know that the speed of a wave can also be written in terms of frequency and lambda. Then angular frequency is 2 pi f, and beta is 2 pi by lambda. Beta is called the phase constant. It is 2 pi by lambda. Now this you should immediately be able to remember your k vector, propagation vector. Okay, so these are some things that I want you to recall. Now, okay, why are we discussing? Why is this chapter there at all? This chapter is there because, first of all, it is simply because wave or propagation of wave is so important, because it is a wave carries information, it carries energy. Okay, how we use it depends on the frequency. When we are going to higher frequencies, we are talking of using electromagnetic propagation for transmission of information. Whereas when we are talking of low frequencies, we are mainly talking about transportation of energy. And I've given you some examples. Radio waves, for example, TV signal, radar beams. Okay, radar beams, for example, it's purely high frequency and it is for information. Then, what are the three important things that you should remember, or the three fundamental characteristics of energy transmission. The first thing is you should remember that energy will get transmitted at the speed of the wave. Energy will get transmitted at the speed of the wave, and the highest speed that you can have is the speed of light, okay, which is c, and that will be the speed of propagation when you are talking about free space. Okay, next thing is when a wave is carrying energy, the energy assumes the property of the wave. So when I'm saying assumes the property of the wave, I may be talking about the frequency, okay, or the amplitude. Square of the amplitude will be proportional to the energy, or the energy of the wave is proportional to square of the amplitude of the wave. So that way it assumes the property of the wave. And thirdly, if you have a source of the electromagnetic wave, the energy will radiate out. The energy will radiate out from the source, and it doesn't require a medium for propagation. Meaning, if there is a medium also, it can propagate, but it does not really require a medium for propagation. Like for example, you're talking of propagation of energy in free space. Okay, so these are three important fundamental characteristics of energy transmission. Once we are done with this, I want to talk about classification of medium. Please remember guys, I will be talking a lot of theory because the fundamentals we have to put before we start solving problems. Okay, so let's start talking about what would be the four types of electromagnetic medium. When we talk of propagation, we talk of four types of electromagnetic, four types of medium. So the first medium is free space. Free space, you all know, okay? And what would be the characteristics of or constitutive properties sigma, epsilon, and mu for free space? It will be sigma equal to 0. Conductivity is definitely 0. Epsilon equal to epsilon naught and mu equal to mu naught. Now, we will go to dielectrics. When we are talking, dielectrics are materials or medium which don't have a conductivity. So that's a general description of dielectrics that you have studied previously. But here we are talking of two types of dielectrics. We are talking of two types of dielectrics. The first type of dielectric that we will discuss is the lossless dielectric. What is a lossless dielectric? The name itself conveys what it's trying to say. Okay, when we say lossless, we are talking about a dielectric medium through which if you pass an electromagnetic wave, there is no attenuation, there is no loss of power, there is no loss of amplitude. Are you understanding? So a lossless dielectric is one through which if you pass a wave, there is no loss. That's why it's called lossless. Loss of what? Loss of energy or loss of amplitude of the wave. That's a lossless dielectric. And what are the constitutive parameters? Sigma will be 0. That means it is not going to conduct at all. It is a pure dielectric. Another name for lossless dielectric is a pure dielectric. It's sigma equal to 0, epsilon equal to some epsilon r into epsilon naught, where epsilon r is called the relative value of epsilon. It can take values like 1, 2, 3 or 4.3. Okay, so epsilon r into epsilon naught, that is your epsilon. Similarly, mu is not mu naught, it can be mu r into mu naught, and this is very important. This you will understand as we go along why this is written. Okay, sigma will be much less than omega epsilon. Sigma will be much less than omega epsilon. Omega is the angular frequency of the wave. Epsilon is of course the property of the medium, and sigma is conductivity. So this should be necessarily satisfied if it is a lossless dielectric. Next, let us go to lossy dielectric. Lossy dielectric is also a dielectric, but as the name suggests, there will be attenuation. Attenuation means loss. Okay, so there will be attenuation of the wave. What is attenuation of the wave? Attenuation means amplitude of the wave will fall. Amplitude of the wave will fall as this wave passes through the lossy dielectric. Okay, and loss of amplitude means loss of energy. Okay, that's why it's called a lossy dielectric. And a lossy dielectric is not a pure dielectric. Lossy dielectric is not a pure dielectric. A lossy dielectric, as you can see here, will have sigma not equal to 0. That means it will not be like a conductor. It will not conduct like a conductor. But then there will be a small amount of conduction happening. A small amount of conduction will be there. Okay. I don't know how many of you will remember that. If you leave a capacitor, you must have studied this in electromagnetics in your years. If you charge a capacitor and leave it, okay? With time, it gets discharged. Very slowly though, but it will get discharged. Why is it getting discharged? It is getting discharged because between the plates of the capacitor, you have the dielectric. Ideally, the dielectric is not supposed to allow any charge to go from one plate to the other. Charge going from one plate to the other means you are discharging it. Okay, but then that should not ideally happen. But then the dielectric material between the two plates will allow a small amount of leakage to happen. And depending on the leakage, what happens is after, let us say, a few days or after a month or so, the capacitor would have got discharged. So this is actually a true dielectric, how a true dielectric will behave. Whereas a lossless dielectric is an ideal dielectric. So a lossy dielectric, on the other hand, is not a pure dielectric. If you have all studied this subject called SPM, right? Structure and properties of materials. So there you must have talked about, have you studied this paper, Structure and Properties of Materials?
Yes, ma'am.
Yeah. So there you must have talked about crystallites and things like that. Okay. So what happens in a lossy dielectric is the lossy dielectric will have tiny crystallites of conductor embedded inside the dielectric. There will be tiny amount of conducting material embedded within your dielectric. So as a result, you must have studied in SPM that there can be losses, okay, at the boundaries the of the crystallites. At the boundaries of the crystallites, you've seen that there can be losses. I'm sure you have studied this. Okay, so that's what happens here also. There will be losses happening at the boundaries. That's why it's called lossy dielectric. And if you look at what are the properties, sigma is not going to be equal to 0, epsilon is not epsilon naught, mu is not equal to mu naught. Now finally, let's go to a perfect conductor. Again, a perfect conductor is also a concept only. You don't have anything called a perfect conductor. But if the sigma is very, very high, then you call it a perfect conductor. Simple. And if it's a perfect conductor, resistance has to be 0. Resistivity has to be 0. You know that is not true. Okay. So when the conductivity is good, you assume it is perfect conductor. Now let us look at the constitutive parameters. Look at the constitutive parameters here. Sigma is infinity. You all know that sigma is not infinity. Okay, but then if sigma is pretty high, you take it as infinity. Sigma is infinity. Epsilon will be equal to epsilon naught. Mu will be mu r into mu naught, meaning you can associate. See, this is actually the irony, conductor, when you're talking of conductor, you're talking of conductivity, you're talking of movement of charges, yet epsilon can be treated as epsilon naught, but mu is not equal to mu naught, meaning these materials, all these conductors have a certain magnetism associated with them. Okay, so mu is equal to mu r into mu naught, and this is important. Sigma, because your conductivity is large, sigma will be much, much greater than omega epsilon, and omega is the angular frequency of the wave. This is a very important concept because you're going to use the consequences of these four classifications and their properties will be occurring again and again, and then you'll see the consequences in the form of how the wave propagates. Are you clear, Sri Chakra?
Yes, ma'am. Clear.
Yeah, all of you are clear. Initially, you may be wondering, how do we remember sigma less than omega, much less than omega epsilon? Okay, I will tell you. For each of this, there is a trick. I will teach you that as we go along. Okay, now let us. What we will do here is this lossy dielectric is the most general case. Okay, lossy dielectric will be the most general case. We have to first do lossy dielectric. Once you understand lossy dielectric, then slightly apply some condition. Immediately you will get your lossless dielectric and free space. Easily you will get it. Okay, so we'll start with lossy dielectric. Okay, so I'm putting it in a block here. You can see I have put it in a box there. I've used different colors and symbols and boxes to highlight what is important and what should stand out when you are learning. So you can see sigma is not equal to 0, epsilon is not epsilon naught, mu is not mu naught. Okay, so this is going to be the most general case for us, and using this, we are going to derive for the lossless and for free space. Okay, for all those things we can easily derive. Okay, as I told you, a lossy dielectric is partially conducting medium. Okay, it is an imperfect dielectric and it is neither a good conductor. So it's an imperfect conductor and it's an imperfect dielectric, but it is mostly dielectric, as distinct from a lossless dielectric, which is a perfect dielectric. Okay, and again, this is again a repetition. A lossy dielectric is a medium in which the electromagnetic wave will lose energy, it will lose amplitude, or it will lose power. Okay, so now in all our discussions, we will be dealing with linear, isotropic, homogeneous materials. Linear, isotropic, homogeneous materials. Okay, so let's start off with the lossy dielectric. We start off with the lossy dielectric satisfying all these three. And you also assume that there is no charge, there is no free charge. Okay, now what we do is we start with Maxwell's equations. Okay, we start with the 4 Maxwell's equations. In case you're wondering why madam has used so much of color, you will realize as I go along. Okay, we will use the 4 Maxwell's equations in the phasor form. What we did last chapter, and you are wondering why I have done it, is going to be used here. Okay, we will do it in the phasor form. In the normal harmonic form, this equation should have been, equation 1a should have been Gauss law, del dot E equal to, anyone? Or del dot D equal to?
Rho V.
Yeah, rho V. Okay. But because there is no free charge, the right hand side becomes 0. And then so it was like this. So ultimately you should have got del dot E equal to 0 or del dot epsilon E equal to 0. Okay, so epsilon E equal to 0 would simply mean that del dot E equal to 0. Okay, and E you have seen can be written as del dot Es and then e to the power of j omega t equal to 0. So what would this mean? This would mean that del dot Es equal to 0. So that's how the phasor representation of Maxwell's equation comes. Similarly, you can go to the next equation, 1b. So what is 1b? Okay, what is 1b? 1b will be del dot Hs equal to 0. This comes from del dot b equal to 0. Now go to the third equation. The third equation, as you can see, is your Faraday's law. Okay, and Faraday's law, if you remember, was written as del cross E was equal to minus dou, anyone? Dou B by dou T, remember? Okay, now here what I want you to do is this can be written as minus B is equal to mu H, so minus mu dou H by dou T. Okay, now look at this. H vector can be written as Hs vector e to the power of j omega t. Now, if you do dou H by dou T, what will you get? If you do dou H by dou T, what will you get? You will get j omega, and then you will get hs. Okay, or you will get hs into e to the power of hs into e to the power of j omega t. Is the step clear? Harmonic vector h can be written as hs phasor into e to the power of j omega t. Okay, what will be dou h by dou t? Dou h by dou t, you can see will be, you will be differentiating only this e to the power of j omega t. So you get j omega hs into e to the power of j omega t. Okay, now go to the left hand side of the equation. Left hand side of the equation, you will have del cross es e to the power of j omega t, and the right hand side has now become minus j omega hs e to the power of j omega t. E to the power of j omega t will go on both sides. So are you able to see how you are getting this 1c? Guys? Girls, I want some girl to answer.
Ma'am, you missed the new
Yeah, mu, of course, there is a mu.
minus j.
No minus. It will be plus only
No.
because it e to the power of j omega t. So mu will be there. Okay, because already, okay, here I should not put the mu. Here I should
Hmm.
not put the mu. I should put the mu, right. I should put the mu here. Yeah, there was
Yes,
a
ma'am.
mu here, right. Okay, I hope now it's clear how these equations are coming. So phasor representation is what we are going to use throughout this particular chapter. Now similarly, go to the next equation. What will be the next equation? Del cross hs is equal to, if you remember, so that comes from the equation del cross h equal to j plus jd. Okay, same logic. Same logic. J is equal to sigma E. E, you will write it as Es into e to the power of j omega t. So e to the power of j omega t will get cancelled out from both the sides. And whenever you are doing a differentiation with respect to time, you will have one j omega. Okay, and whenever you are doing an integration, you will get the j omega in the denominator. That's all. Okay. So I hope this part is clear to you. Okay, now if this part is clear to you, let us, why I have used different colors also you will understand in a few minutes. Okay, so now what we will do is, let us take our equation 1c. What is our equation 1c? Equation 1c is Faraday's law. Take that phasor equation and take curl on both the sides. Now you understood why I took green there, so that I can avoid writing a lot of things. I put green there. So you have taken that green equation and then you have done curl on both the sides. Okay, and because it is a homogeneous and linear isotropic material, this omega, mu and all can be taken out of your curl. So you get curl of Hs. Is that clear? Okay, once you've done that, let us solve the left-hand side. Left-hand side you can see is del dot Es minus del square Es. Now come to the right-hand side. Right-hand side is remaining as minus j omega mu del cross Hs. Okay, now if you are wondering why I have used the blue color here, I'm just going to take this. I'm just going to take this. So what is my del cross Es? I'm sorry, del dot Es. Del dot Es becomes 0 because of 1A. And similarly, come to del cross Hs on the right hand side. Del cross Hs I have written in red color because I am going to use 1D. I'm going to use 1D, and instead of del cross Hs, I'm going to write sigma plus j omega epsilon Es. Is this clear to you guys? We have just taken Faraday's law in the phasor form. We have taken curl on both the sides and then substituted equation 1a and 1d into that. Some chat. What is that? Yes, ma'am. Okay, Shantanu, good. Okay, so this is what we are doing. And once we do this, okay, look at the left hand side and the right hand side. It is a function of ES. It has got only ES on the left hand side and on the right hand side. Okay, so now what we are going to do is we are going to rewrite this equation, okay, or multiply the left hand side and right hand side by -1. So you are getting del square ES, and bring this fellow from the left hand side, from the right hand side to the left hand side. So you get, or I will do it and show you, I'll show you what you will get. You will get del square ES, okay, del square ES, and then bringing this fellow this side, you will get, because you already multiplied by -1, okay, so therefore this will become minus j omega mu into sigma plus j omega epsilon ES, okay, equal to 0. Now this entire thing, I am going to put it into a square bracket. Okay, and what do I do? After putting it into a square bracket, I'm going to call it as some gamma square. You're going to call it as some gamma square. Therefore, you are getting equation 2a. Okay, so what is equation 2a? Del square ES minus gamma square ES equal to 0. Now, this gamma, you have written gamma square. Okay, this gamma is called the propagation constant. It is called the propagation constant. And if you look at what are all going into making this propagation constant, you can see that gamma is a function of omega, which is a property of a wave. It is a function of mu and epsilon, which are properties of the medium. It's a function of sigma, which is the property of the medium. Or you can simply say that the propagation constant depends on the constitutive parameters of the medium. It depends on the constitutive parameters of the medium and the angular frequency of the wave. That means it involves the property of the wave and the property of the medium. That simply says that how a wave will propagate through a medium depends on the property of the wave, and it depends on the property of the medium. So that means in different mediums, waves will propagate differently. Okay, and it is a constant for a given wave and a given medium. That is why it's called a propagation constant for that combination. Okay, when you change a wave or you have another medium, you will have another wave. Okay, it's called the propagation constant simply because it is a constant for a given combination of a wave and a medium, and it is going to tell you something about how the wave will propagate. So propagation constant gamma depends on property of the wave and the property of the medium. Is that clear, guys? And you should also know what are all the properties it will depend on. It depends on omega, it depends on epsilon, it depends on mu, it depends on sigma. Okay. Now, instead of doing it this way, if I had started, instead of doing it this way, if I had started with 1D and then done the required substitutions, then I would have ended up with a different equation. That equation would have been del square ES. That equation would have been del square HS minus gamma square HS equal to 0. Or you would have got an equation in terms of magnetic field. Or you have equation 2. Equation 2 is consisted of equation 2a and 2b. Okay, one is written in the form of electric field and the other written in the form of magnetic field. Now you have come across equations which look similar to this. Anyone remembers? Not the same equation, but which looks similar in the previous chapter. If you're studying, you will remember.
Potentials.
Potentials, yeah. There we have written two equations, remember? And we call them as wave equations. Wave equation for scalar potential and wave equation for vector potential.
Vector potential.
Yeah, then we talked about the solution for those two wave equations. The pattern will be the same. Only thing is different ways we will be talking about the same concept. So similarly here, instead of talking about scalar and vector potential, which will indirectly lead you to electric field and magnetic field, here we are talking of Maxwell's equation. I'm sorry, we are talking of wave equations which have a name. They are called Helmholtz equation. Mathematics, you must have studied Helmholtz equation. So these are called Helmholtz equation, okay, and they are also called wave equations, and they are wave equations for electric field and magnetic field, unlike what you have seen for vector potential and scalar potential. Okay, next. Now, what do we do with these equations? Obviously, we have to find out the solution. What is the meaning of finding solution? Finding solution means finding out H and B. Okay, so let's go ahead. So we made this substitution. Gamma square is equal to j omega mu sigma plus j omega epsilon. We had made the substitution. Let us open up the bracket. When you open up the bracket, you are getting minus omega square mu epsilon plus j sigma omega mu. So this clearly has a real part and an imaginary part. That means it is not purely real. It is a complex quantity. Square of propagation constant is a complex quantity. If the square of if gamma square is a complex quantity, this also means that gamma is complex. Yes or no? If gamma square is complex, then gamma also has to be a complex quantity. Okay, so what we will now do is, let us assume that this gamma is some alpha plus j beta. Don't think, what is alpha, beta and all that, how does it? They are all going to have a meaning. They are all going to have a meaning. Right now we are doing some mathematics, but they all have a meaning which will become clear as we go ahead. Okay, there is a physical significance for each of these terms. So this propagation constant gamma is written as alpha plus j beta. Okay, alpha is a real part and j beta becomes the imaginary part. So now what we will do is, let us square gamma. If you square gamma, what will you get? Alpha plus j beta into alpha plus j beta, which without even putting a paper, you will know is alpha square minus beta square plus 2j alpha beta. Alpha square minus beta square plus 2j alpha beta. Please remember, here you are making an assumption that alpha beta are both real. Okay, but gamma is complex. Now what you do is, okay, so let us take the real part of gamma square. Let us take the negative of the real part of gamma square. Which is the real part of gamma square? The real part of gamma square is alpha square minus beta square. So I want the negative of the real part. So the negative of the real part will be beta square minus alpha square. It will be beta square minus, you can see here, it is beta square minus alpha square, and it is a negative, right? So go to this expression. Here also you already got your gamma square. You want the negative of the real part. So negative of the real part will be minus of minus will become plus. So it will become omega square mu epsilon. Guys, did you understand this? First equation, the green equation we have written directly from the substitution of gamma equal to j omega mu sigma plus j omega epsilon. Then after that we are saying that gamma is complex. So we will call it as some alpha plus j beta. Then from that we will get the real part. Negative of the real part is beta square minus alpha square, which from the previous equation becomes omega square mu epsilon. So let's call it as equation 3. Okay, now our aim is going to be to evaluate alpha and beta first of all. If you evaluate alpha and beta, you will get gamma. Okay, so the first step is getting beta square minus alpha square. Okay, once you have done this, I want you to find the product of gamma and its complex conjugate. Find the product of gamma and its complex conjugate. So what will it be? Alpha plus j beta into alpha minus j beta. When you do this, what will you get? You get alpha square plus beta square. Here you got alpha square minus beta square. Here you will getting alpha square plus beta square. Now we need to know what alpha square plus beta square is going to be. So for that, what we will do is take gamma. See, so this is slightly complex. Just try to understand, guys. Okay, you want gamma into gamma conjugate. So what we will do is, you already know gamma square, right? Take gamma square and complex conjugate of gamma square. Take gamma square and complex conjugate of gamma square. multiply and get the under root. Okay, when you get the under root, what is it you are indirectly getting? You are getting gamma star. Is this step clear, guys? Any doubt? So I'll tell you the crux of it is this much. I want to get my alpha and beta. To get alpha and beta, what I'm doing is first I'm getting beta square minus alpha square. Okay, next I'm going to get beta square plus alpha square. Between them, I can use them as simultaneous equations and solve beta and alpha. So that's what you're trying to do. Okay, so here you could write your beta square minus alpha square in terms of the original properties. Similarly, we want to get beta square plus alpha square. So for that, what do? You only have gamma square. Okay, so get your gamma square and the complex conjugate of gamma square, multiply and get the under root. So that is the same as gamma into gamma conjugate. Okay, so what do? Gamma square into gamma square conjugate. So what will this become? This will become omega square mu epsilon square. So that is omega to the power of 4 mu epsilon to the power of 2. Similarly, here you will get gamma omega mu square, and I want under root. So put your under root also. Take out the common parameters. So what is common? Omega mu. One omega mu you take out. When you take out one omega square mu square, you will get sigma square. This sigma square you will get. And the other thing you get is omega square epsilon square with an under root. This part is going to be used again and again. So please go through these steps. I will give you half a minute. And if you have any doubts, ask me. You've written gamma square in terms of the properties of the medium and the wave. Next, you're seeing that gamma itself is complex, so you're going to call it as some alpha plus j beta. Then write gamma square in terms of alpha and beta. Then take the real part and multiply by a minus so that you are getting beta square minus alpha square, which is omega square mu epsilon. Similarly, you want beta square plus alpha square. To get that, what you need to do is you have to get gamma into gamma star. But in terms of the properties of the medium and the wave, you don't have gamma, you're having gamma square. So what you do is take gamma square, multiply by gamma square conjugate, and then take an under root. So that's all we have to. Is that clear? So equation 3 and 4, you can see one is beta square minus alpha square, the other is beta square plus alpha square, simultaneous equations. So if you add them, what will happen? Alpha square will go, you get 2 beta square. Similarly, if you subtract 3 and 4, what will you get? You can get rid of beta and then get your alpha. Is that clear? So you're going to use equation 3 and 4. So I'm not, you don't think just because I put the answer, it is a complicated thing or anything. Okay, just elimination of for equation 5 to get beta, what I've done is I've eliminated alpha. To get equation 6, we have eliminated beta. That's all. Okay, and this equation looks complicated. Yes, it is complicated. As you keep working out problems and writing it again and again only, you will be able to get used to this. Okay, otherwise it's going to be difficult. You will have to write it again and again so that you get used to this expression. Because you're going to use this expression many times. Okay. Now what are all involved here? Omega. Then of course there will be a 2 there because you get either 2 beta square or 2 alpha square. So there is going to be a 2 and an under root. Then mu epsilon is having a unit of inverse of velocity. I'm just trying to tell you how to remember this. Basically, I'm just trying to tell you how to remember this. Omega will be out of the under root. Then divided by under root 2 is definitely going to be there. That is logic. Then mu epsilon will figure, which is having the speed of inverse of speed you will get. And then inside the bracket, square bracket, you're going to have 1 plus sigma by omega epsilon, okay, square. Here also you have 1 plus sigma by omega epsilon square with an under root. For both of them, it is common. And when it is beta, you have a plus 1, okay? And when it is a gamma, and getting your alpha, you will have a minus 1. That's the difference. If you remember one, you can get the other. For alpha, it will be a minus 1. And for beta, it will be a plus 1. Now, this also I will tell you how to remember. Alpha in some cases can take 0 values. Alpha can take 0 values, but we are going to see. Alpha can take 0 values. So that means this minus 1 is justified. Logically, there is a minus only now, you can actually get rid of some terms. So this minus 1 is justified. Whereas beta can never take negative, it can never be 0 there for this plus 1. Okay, remember this. Is that clear, guys? I know it's a lot. So I will stop here. This would be a logical place for me to stop. Okay, go through this and come. Next, what we will do in the next class is we will consider a wave propagating along the positive z direction, and the electric field is going to have only the x component. We will take such a wave and then apply this theory to that wave, okay, and get the solution for Helmholtz equation. You remember a Helmholtz equation. So you take your Helmholtz equation and apply this condition and get your solution for Helmholtz equation, or get your solution for the E vector, the electric field vector, assuming that the medium is a lossy dielectric. Is that clear, guys? Now when I'm talking, it's all Greek and Latin. So unless we do it, you won't be able to understand. All I want you to do when you come to the next class is this 5 and 6, please learn and come. And once we go ahead, after that, it won't be difficult. The real difficult maths is only up to this particular point, up to equation 6. This was a derivation. After that, things will go smoothly. Okay, that's why, because it's a tough part only, I did it slowly, and next class we can go a little fast. And another thing also that you would, I don't know how many of you noticed, I said Helmholtz equation, and if you look at Helmholtz equation here, you see the way it has been written. It is written as not del square. It is written as dou square by dou z square. Why is it written as dou square by dou z square? Because your electric field, we have said, is having only the z component. You can differentiate only with respect to z. And then it is a function of x. Is going to be a function of x. The wave is traveling along the z. I'm sorry, I think I made a mistake here. Okay, the wave is a function of z. It's a function of z, but it is having only the x component. Why do I say function of z? Because it is traveling along the z axis, but it has got only the which component? It's got only the x component. So that's the reason why we are writing dou square by dou z square. And then of course gamma is, and let's see how to get the solution in the next class. Okay, I hope it's clear. If you have anything, please put it in the comment immediately or tell me.